I can get you to do some work to get some idea. Any questions before we start?
Sir, I had a slightly longer question to ask about characterizing C1 functions. Should I ask it now or at the end of class?
Why don't you just why don't you just state it and then we will see. So.
Okay, sir. Sir, I worked through the proof using arbitrary bases for Rm and Rn instead of the standard ones, and
Okay.
it seemed that the proof worked with a small modification near the end.
Yeah, so maybe we can discuss this later. Okay.
Okay, sir.
So,
yeah.
All right. So,
sure, sir.
all right. So while on the topic, so what characterizes a C1 function? That is a function, a multivariable function. If it's, what does it mean to say that such a function is C1 on some open set U in the source Euclidean space? Come on. So this just a matter of definition, and it's a major definition, so you should know this.
We mean that the derivative exists at all points of view, and the derivative as a function itself is continuous.
Is continuous, right? Okay. And this derivative function is from where to where?
U to the space of linear maps from Rm to Rn.
Correct, exactly. So that is the definition. And by iterating, we can get definitions of higher C classes. That is continuously differentiable, that is C1, continuously double differentiable, C2, and so on and so forth. And C0 is just continuous. Okay, and what is the characterization of C1 functions? A function is C1 if and only if on an open set U, if and only if all of its partial derivatives are defined everywhere, exist everywhere on U, and
are continuous.
Okay, so now with this in mind, let's look at this example. Examples 1. So this is a function from R2 to R. So it's going to be defined as this one. It's a fairly standard example, but we should work it out. So of course, this function will be defined, the expression as I have written will be defined for every value of, for every point except the origin, right? So this is when x and y is not the point 0 and 0. And then I'm going to define it as at the origin like this. So there are several functions, there are several things which I want you to do. Is f continuous at, well, it is going to be continuous everywhere, right? Except the origin quite easily. Because why is it continuous everywhere at the origin automatically?
Because the denominator is non-zero.
Right.
Always, and it's quotient.
Quotient of what?
So of continuous functions.
Right. So it's a quotient of continuous functions. And those functions are continuous because x and y being projection functions, they are continuous. So their product is continuous. And xy is continuous, as is x square and y square. So their sum is continuous. And square root function is continuous for non-negative reals, which is where x square plus y square is landing, etc. Right? So continuous at the origin. So obviously continuous elsewhere. So the answer is yes, f is going to be continuous at the origin. So I want you to see why. Then what about partial derivatives? Okay, so why don't you get started with these questions? Right, so I'm going to give you a few minutes. Actually calculate. All right, so next Monday in the quiz, I should tell you there is going to be calculations. Uh, so this is some practice for that. And on the homework also, you are asked to practice, do a bunch of them. I don't know if you have gotten to that, but here's where you can get started. So a few minutes, and as soon as I have somebody has something for the first one, you can tell me, and I'll write down the answer.
Sir, for the continuity portion at origin,
Yes.
uh, if x is not equal to 0, I mean, if x comma y are simultaneously not 0, then we can just substitute them to be equal. I mean, if we try to see them along a line, I mean, y equal to x, and then we can judge its continuity by for x comma x not equal to 0 simultaneously and the 0 at a point.
Okay. So is that enough to conclude that something is continuous?
No, sir, that is one direction actually.
Right. So if you are saying that the function is not continuous, then it is enough to show by approaching along some direction and showing that it is not continuous as a function along just that direction. But in this case, it is actually continuous. So what you said is it can be a test, but it is not going to be a proof.
Yes, sir.
Okay, so let's name these. So 1, 2. So what do we need in order to show continuity?
Sir, I think I have something. Should I say?
Yeah, just go ahead.
Okay. I think we to show that to show continuity, we'll pick some norm, and under the norm, we need to show that as the modulus of or the norm of x comma y gets very small, then the norm of the function also gets very small.
Right, very, very small because you want it to go to 0, right?
Yeah, if we want to show that it is, yeah.
Okay, all right. So let's write this down. Um, uh, so what we want to calculate is this, no? F of x comma y minus f00. Now I can say norm, but you see this is a function from R2 to R. So it's just absolute value, right? So what we want to show is that this goes to so want.
Sir, I think I have an observation to tell.
So let me just finish writing this and then I'll just. So
Okay.
this goes to 0 as x comma y goes to 0. Okay, all right, go ahead, please.
Right. So xy divided by square root of x squared plus y squared, we can prove that that is less than or equal to square root of x squared plus y squared divided by 2.
Okay, all right, so let's write this down. So xy divided by square root of x square plus y square. And so this is really just absolute value of that, right? That's what um, so this is just equal to that. And I should take absolute value of everything, but really the denominator doesn't really matter. So I can just say, okay, I'll write down absolute value of everything. Okay. So now what you are saying is that this is less than or equal to. Yeah, say that again, please.
So square root, I mean absolute value of square root of x squared plus y squared divided by 2.
Okay. So I should probably record. Yeah, so just stare at this and see if this is true.
Recording in progress.
Okay, so we are trying to show that this function f, which is defined from R2 to R, is continuous everywhere. At places other than 0, it is made out of continuous functions where the denominator is non-zero, so it is automatically continuous. by standard result. So we are just checking at the origin. All right, so I have calculated the difference between f of x comma y non-zero and f at the origin, which is 0. And we want to bound this difference. If we show that what it is bounded by goes to 0, as the point x comma y goes to 0, then I'm done, right? So do you see where the inequality is coming from? Do you agree? Right? I mean, this is just coming from the fact that x minus y the whole square is greater than or equal to 0 always. Okay. And what happens to this?
So if we take the P2 norm at x comma y.
Right. So exactly. But I mean, any norm is going to be okay, right? So the point is that
Yes, sir,
this
actually the P2 norm,
0.
I mean, we can directly see it.
So this goes to 0 as x comma y goes to 0. And yes, so if you want to write down an actual epsilon and delta, then we can do it using the right hand expression, and then the usual Euclidean norm will do the job easily for us. Okay, so this is all right. So number 1 is done. So now question 2. So do the partial derivatives exist at the origin, and do they exist elsewhere? What about elsewhere?
Partials do exist outside the origin because it's just one variable calculus.
Exactly. So it's just one variable calculus, right? So in fact, what I would like you to do is calculate these partial derivatives. So calculate all right. So so go ahead. But before that, what about del f by del x at the origin and both partials at the origin?
Both are 0.
Both are 0, right? So let's just see one. Okay. So what do I have to do in order to do this? So this
So
is
just the
limit
limit
as
h tends to 0 f of
correct.
h comma 0 minus f of 0 comma 0 by h.
Right? You're just straight away just using the definition, correct? So what is that equal to? Just see. What is f of h comma 0? Come on.
0.
This is just 0, no? Because I have multiplied x and y at the top. So this is just 0. So this is just limit as h approaches 0 of 0 minus 0 by h, which is equal to 0. And in exactly the same way, similarly, is also equal to 0. All right, so now I will just say, so maybe this is number 3. And this is just note, really, there is nothing else. So I would now like you to do this Roman numeral number 2 and actually calculate. And then once you do the calculation, I want you to see why I'm asking you to calculate that. Okay. So you should just get started. And maybe I will just stop recording because we don't want to have a gap. But so get started, please.
Recording stopped.
Yeah, so as soon as somebody has the answers, just let me know. Here is the function once again.
It's y cube divided by x square plus y square whole to the power 3 by 2.
Okay, so say that again. So this is which derivative?
Uh, Partials with respect to x direction.
Answer to 2. Yeah, so say that again. This is what do you have at the top?
Y cube.
X. Y cube, right? So y cube divided by
X square plus y square
x square
to the
plus
power 3 by 2.
Okay. And how does one do this?
Chain rule, I mean, just one variable, I mean,
Just one variable calculus. So basically what you're going to do is you're just going to take the formula as given and regard y as a constant and then just do it, right? Because we have shortcut rules now. In the one variable case, a well-trodden ground that you have done for years. Okay, so let me write down the answer to del f by del y. And this is going to be exactly symmetric, no? So what will the answer be?
x cube divided by the same denominator.
Correct. Okay, so just 1 second.
Recording in progress.
All right, so we have these answers. Now we look at number 2 and number 3 together and actually now consider the derivative. So now question 4. Is f differentiable at the origin and elsewhere? What about elsewhere at a point away from the origin? Is the function differentiable?
Yes, because it's the ratio of two, I mean, nice functions.
What do you mean by nice?
I mean, differentiable functions.
Ratio of two differentiable functions. Okay. How about using our criterion? When do we know that a function is? How do we check that a function is differentiable?
We can compute the partials and check if they are locally bounded.
Okay, but in fact we have something more. No, we can just see if the partial derivatives are continuous functions at any given point. Then not only will the given function be differentiable, but the derivative itself will be continuous. So it will be more than differentiable.
Yes, yes.
Right. So you look at the partial derivatives away from the origin, and the formulas are written right there. What do we know about those partial derivatives? At any point that is different from the origin. Well,
They're continuous everywhere else. Product of quotient of polynomials.
Right. So not polynomials. Yeah. I mean, you see, there is that 3 by 2 that is going to make life interesting. Right.
Yeah, but that is still continuous. So
but it is still continuous everywhere. Everywhere else, it is going to be everywhere else. The partial derivatives themselves are continuous. So we know that the derivative exists, and in fact, the derivative itself will be a continuous function everywhere. What will be the matrix of the derivative? What will be the size of the matrix? At any point x comma y, which is different from the origin, we know that the derivative exists because the partial derivatives exist and are continuous. So what will be the derivative of the matrix? What's the size? Come on, this is easy.
1 by 2.
Right, exactly. So this is a function from R2 to R1. and therefore the matrix of the corresponding derivative will be given by a single row, right? Which is what a linear function from R2 to R1 is encoded by. But now we come to the interesting part. What happens at the origin? Okay, suppose the derivative did exist at 0, comma 0. What would it be then?
The zero matrix.
Yeah, right. So the derivative would have to be the zero matrix. Can you take this thought further and maybe make some tests? Anyone? So what somebody said earlier, now we can apply that idea and start coming through various directions, right? See, if f prime does exist, then that means that not only must the two partial derivatives exist, but the derivative must exist along any direction. So look at the function and see if you can think of an interesting direction along which we can test this.
The direction x equals to y works.
Right. And let us see what happens. So here, if f prime 0 exists, then let's not even say its matrix, then its matrix must be the matrix. Okay, let me write this as a square bracket. Just the matrix consisting of two zeros. And therefore, as a linear operator, it must, it must map any vector to 0. In other words, the directional derivative along any direction must be 0. So it must be the 0 operator. That means that dv of f at the origin must be 0 for any direction, for any vector v. So let's test. V is equal to which one?
1, 1.
1, 1. Okay. So now I'm not quite sure how to write this. Let's write this as a column vector maybe. 1. So what do we do?
We compute the limit along that direction and then show that
And
it's
then what happens?
It is 1, I think.
So dv of f at the origin. What do I need to do? F of 0 plus tv minus f of 0 divided by t or h, doesn't matter, limit as t approaches 0, correct? So what do I get?
I just substitute in the function and then we
Correct.
can
So
compute the limit.
exactly. So f of 0 is 0. So now just tell me. So f of I have t comma t divided by t limit. So what is f of t comma t?
T.
So f of t comma t, what's the formula? So that is right. So I'm going to get also this root 2, but doesn't matter. The point is that so t square divided by, what do I get? T square divided by square root of 2 times t square, correct?
Yes.
Right. So of course I'm calculating limit as t approaches 0. And the point is that this is not equal to 0. Right. And if I, by the way, if I scale this vector, sometimes when you say direction vector, when we take the unit vector, right? I didn't really take the unit vector. But no matter what, if I scale this vector to any non-zero vector, I'm still going to get a non-zero. So what is the conclusion?
The function is not differentiable at 0. At the
And
origin.
therefore, what must happen about the direction, about the partial derivatives? Thus, f prime 0, let's write this vector, f is not differentiable at 0. Therefore, what can I say about the partial derivatives at 0? What must therefore necessarily happen?
They are not continuous.
Right. Well, a priori, it's not true. It's not necessarily true that they're all discontinuous. At least one of them must be discontinuous, right?
Yes, yes.
But in this case, therefore, at least one partial derivative must be discontinuous.
But both are symmetric, so both of them are discontinuous.
So in this case, x and y, I mean, it's a symmetric. If you switch x and y, the function stays the same. So by symmetry, they both have to be discontinuous. So while I'm writing this, can you check that they're actually discontinuous? At the origin, here, both must be discontinuous. Okay, so just check what happens.
If you put x is equal to y is equal to t again, and then take t goes to 0, then you will get some non-zero limit.
No, actually, see what happens. Partial. Okay, so again, let's check. These partial derivatives again are functions from where to where?
R2 to R.
From R2 to R, correct? So continuity, remember, continuity for a function, that means that with, given any epsilon, there exists a delta, etc., etc. But in this delta, I'm allowed to come to the point at which I'm taking the limit from any direction. It has to work within distance delta, even in any direction. So see what happens.
So the x-axis and y-axis, if we approach on those directions, we get different limits.
So can you just explain that?
Yes, sir. If you're approaching along the x direction, then we set y equal to 0, and the limit is.
So one second,
Yeah,
please.
yes.
So which for definiteness, which one are we doing? Are we doing the partial with respect? Let's just see the first one, del f by del x. Okay.
Yes, sir. Yeah.
Okay. So now I am approaching. So I want to test the continuity of this function at 0. Okay. So what do I do?
we first approach along the x-axis, and on the x-axis, the function is identically zero, except for the origin. So the limit as we approach the origin on that line is zero.
Okay, so just let me just see if I understand this. So we are approaching along the x-axis, and so that means that means y is zero. So the function is so this partial derivative is identically zero. Okay, good. And of course, we are not really seeing what the um, by the way, the value of the partial derivative at the origin is also zero. We calculated that separately. Okay, so good. So along the x-axis, this function is just constant, namely zero. Okay, so now what?
Along the y-axis, x is zero, so the function becomes one.
But actually, even there is a little bit. Just see what happens. The function is not really one. Okay,
Is it not
let's
one?
okay, so let's plug in x equal to 0, so that I have y cube divided by y square to the power 3 by 2. Okay, what happens when I plug in, let's say, 1 into this? And it's all good, no? I get 1 cube divided by 1 square to the 3 by 2. That's good. What happens if I plug in -1 into it?
Yeah, we don't get the same thing.
So what do we get in fact?
We'd get -1.
Right. So in fact, we have shown its discontinuity quite more than what is needed. What we said is that along the x-axis, if I approach, then the limit is 0. Along the positive y-axis, if I approach, the limit is 1. But from the negative y-axis, the limit is well
-1. Yeah.
-1, and the value itself is 0 over there. Correct. So any two of these three calculations will do the job. Or in fact, why any two? Just we do not even need to approach along x-axis. Even if I approach along positive or negative y-axis, then the limit is either 1 or -1, but the value of the partial derivative at the origin is 0, right? So it's discontinuous. So let's just say this. So del f by del x approaches or let's say is, let's just write this, equal to 0 at the origin, but equal to 1 on positive y-axis. So it cannot be continuous. Okay. So what is the upshot that conclusion? One of the things is that thus we solve. So this gives an example. Where both, or let's not say both, because this is where all partial derivatives exist, and the function is also continuous. But f prime does not exist. Okay. All right, so that was example 1. Oh, okay, sorry, I just began somewhere else. Okay. Can you give me an example where the derivative exists, but it is not continuous? And what you should realize is that, is this really, do we really have to have a multivariable situation for this?
We don't. There are examples with some
Just
sine 1 by x something, but I don't recall them at the moment. I'll have
okay.
to take 30 minutes.
Okay. So here example where f prime a exists, or not just f prime, just f prime exists everywhere. But is not continuous. So we'll just say recall one variable example. And this is a famous one that you should really know. Okay, so you should use a different letter because I want f. So this is g of x. Okay, so let us see how to bootstrap this, just to recall, and how to. So do you know a function that does? So do you know a function that yeah, so the function to keep in mind is sine of 1 over x. All right, so what happens to this function as x approaches 0? So here is this thing, sine of 1 over x. What happens as x approaches 0? You see, the function sine oscillates every 2 pi. What happens to values of 1 over x as x approaches 0? Let's say from the positive side. Right. So of course, infinity is not a real number. So let's not say converges, but it goes to infinity. And in fact, it increases, right? It increases monotonically. So it will go through, this. So the values of 1 over x will go through, an interval 2 pi over smaller and smaller range of values of x, right? And over every such window of x, such that 1 over x traverses an interval of length 2 pi, sine of 1 over x is going to make one complete oscillation, right? From whatever, a certain value, then up to 1, then -1 and back. So each oscillation is going to happen in a narrower and narrower window, but these oscillations are never going to end. So as you go closer and closer to the origin, you see this function is going to take, no matter how close you go, oscillations between 1 and -1 are going to continue past that. It's going to continue oscillating infinitely. So this function does not have a limit as x approaches 0. And in an interesting way, unlike the situations that you saw in school, where very often where you just said that limit from the left exists, limit from the right exists, but the two limits are not equal. Here, there is no way to, so the limit does not exist for a different reason. But now if I want to make this function continuous at x equal to 0, then what I can do is the standard trick, namely just damp it. So what do I do? If I want the limit of this function to be 0, then all those oscillations I just damp them. So what do I get to do? What can I do?
X.
Just multiplied by x, right? And all of those oscillations, they will die down. So when you do this, when you show that such a thing has a limit, you use the squeeze theorem, right? This function will be bounded by absolute value of x above and minus of absolute value of x below, because the sign term is always between 1 and -1. This function is not going to have a derivative at 0, as you can check. But first, let me make this continuous at x equal to 0, x not equal to 0. All right. However, there is one thing that you can say. This is a continuous function. And but you can check that it does not really have a derivative at 0. And in fact, we can sort of check this. No? If this had to have a derivative at 0, how would you calculate the derivative? just a simple oral calculation, you see. Then I have to do g of h minus g of 0, which is 0, divided by h, and calculate the limit as h approaches 0. All that it does is that in h sine 1 over h, the h cancels out. So the derivative at 0, if it existed, would have to be the limit of sine of 1 over h as h approaches 0. I hope you see what I'm saying, right? But which we just said does not exist. So this function is not differentiable at 0. However, to get a function that is differentiable, I know one tool, which we are not going to be using in this course very much, but you learned it extensively last semester. If I have a continuous function, then I do get to construct a function whose derivative is that continuous function. What do I do? Come on, if...
So can you repeat what you just said?
Yeah, so I said, if I have a continuous function, so here g is a continuous function everywhere. Can I construct a function whose derivative is g? Is such a thing guaranteed to exist?
We integrate.
We integrate, exactly. So, right, so we get to integrate this, and you can see what to, how to maybe integrate this function. But here is one thing which is related to its integral. So this one works, okay? And you can see why. So recall one variable example. So the point is that g prime exists, including at 0. And now you see the same calculation that I did for g prime of 0 is now going to work, because when I divide by h, one, from h square, one h cancels out, but I'm left with h times sine 1 over h, and that goes to 0. G prime exists everywhere. G prime of 0 is equal to 0, but g is not, but is not continuous at 0. So basically what I do is I get to bootstrap this example. So here is the thing. So you should calculate the derivative of g. So define f by f of x comma y is equal to g of, I just take x and y, and let's say x square plus y square, square root of that. So now you should check. F is continuous. Is this easy? Come on.
It's a composition of two functions. Which are
It's a composition of two functions, but what you have to say is it's a composition of two continuous functions, right?
Yes, sir.
So being composition of two continuous functions, so this is easy. F is differentiable. And where do we have to check this really?
Sir, in the above example, g dash is not continuous at 0, right?
Sorry. Yeah, thank you very much. So G absolutely is, it is differentiable. It's G prime which is not continuous. Yeah, thank you for pointing that out. All right, so F is differentiable. Need to check only at origin. So what do you think the derivative is going to be? At the origin, the derivative is going to be again the 0 function. Okay. But you will see that f is differentiable, but f prime is not continuous at the origin. And you can sort of see this by looking at the, so how would you calculate f prime? I mean, what do you use to calculate f prime?
Chain rule.
Chain rule. Okay. So this is fine, but so you have to calculate the derivative of g. Now, when you calculate the derivative of g as a function, remember, I'm calculating the derivative of g as a function in order to check its continuity. So at g prime at zero, so just go back to the one variable situation. So g prime at zero is zero. We just checked that, right? But if I calculate g prime elsewhere, do you see what's going to happen? What is it that is going to contribute to the cause discontinuity? Just calculate g prime and see what happens. We are going to calculate g prime using the product rule. So the first term is going to be 2x times sine 1 over x. Will that cause any problems in continuity?
No, so it's
No. Right? So 2x sine 1 over x will cause no problems because that sine 1 over x is bounded, and x will go to 0. So this is okay. It's the other term where I'm going to take x square times cosine 1 over x, but then the chain rule tells me that I have to multiply this by minus 1 over x square. That will cancel out the x square, and I will just get minus of cosine of 1 over x. And this is again going to cause those wild oscillations from minus 1 to 1, no matter how close I go to 0. So that is what is going to cause a problem. So this is something that I want you to check, but this I leave for you to do. Okay. And 3 is, I will not do the example here. Do last homework problem. But I will do a related problem in on Friday. But really, you should do this for yourself. All right. Okay. So all right. So any questions so far? Very well. So let's go back to Taylor's theorem. Taylor's theorem. I should say one thing. When we did the one variable case yesterday, so remark. So the, how do I want to say this? In the one variable proof, m is equal to 1 case is just, so what was m equal to 1 case? So where the Taylor polynomial is of degree 0 and the correction term is of degree 1. What is that known as otherwise?
Mean value theorem.
Mean value theorem. And so if you see what the proof is, it really is the proof of mean value theorem based on Rolle's theorem. You get to adjust, right? So in the proof of mean value theorem from Rolle's theorem, what do? You have a given function and you simply subtract a line from it so that the two endpoints of that secant that you're considering, they come at the same level, right? So what we did is exactly the same. you adjust. It's just the proof of mean value theorem from Rolle's theorem. This is just to say that the strategy that we followed was a very natural strategy. So Taylor's theorem, multivariable case, let's write this down. So what is the situation? I have a, so this is the situation. We have A belong to an open U in R, and I think we took N here. And we have a function, real valued function F. F is M times continuously differentiable function. Then there is, then for small h, basically I get to write down the value of f of a plus h in terms of the values of f and its derivative at a. Okay. But how small should h be? Small enough. So then there is a neighborhood w of 0 in Rn such that for any h in W, we have this translate of W, which is in U. So I can calculate F and F of A plus H equals. All right, so I do want to write this. I want to write this in quotation marks. So let's first just write the one variable Taylor's theorem. So what will it say? F of A plus H times F prime of, okay. So this is not good. Do it right. Plus F prime of A times H plus F double prime of A times H square. Plus all the way up to 1 over m minus 1 factorial times the m minus 1th derivative of f at a, h to the m minus 1 plus r of h, where one over m factorial times the mth derivative of f, but not at a, times h to the m. So a plus theta h. And for some theta strictly between 0 and 1. Okay, so all of this is within quotation marks. In the last class, I said that there is a way in which I can understand this formula as being valid even in multivariable case. But let us write this down more explicitly. So what is the claim here? But need to make sense of this. More explicitly, So it's the sum of partial derivatives, ith partial derivative applied SI times, where these multiplicities add up to k divided by S1 factorial up to Sn factorial. And all of this is, of course, applied to the function at a. Okay, so of course you understand this is not f applied to a, that's just a constant, and then I don't take partial derivatives, that would be zero. It is though that partial derivative of f evaluated at a multiplied by h1 to the s1 all the way up to hn to the sn plus r of h, where r of r of h, in fact, let's do this. Where r of h equals exactly the same thing, summation s1 to m now, and the exact same thing d1 to the s1, this partial derivative but notice that these ss now are adding up to one more, they're adding up to the highest degree under consideration m, but this partial derivative is of f, not applied to a but to some point between a and a plus h. So I will just say plus theta h for some theta strictly between 0 and 1, and then the same terms h1 to the s1 up to hn to the sn for some theta strictly between 0 and 1. Okay, so this is a mouthful, but we saw that so this is the statement, Taylor's theorem statement, and let's see what we can do. Proof. So we saw that the strategy was quite simple. I mean, you just apply the one variable theorem after pre-compose, just put a straight line between the two. So what this has ensured, okay, so let's just look at the hypothesis. Okay, so let's draw a little picture over here. This is A, and I have something over here. However, what I can do is I can put some ball around this. So this is A. So this is U. And what is this set that I have drawn over here? This ball. This ball is not W. It is A plus W, because W itself is a neighborhood around 0. So I have just translated it. And here is going to be A plus H. So I'm just going to restrict this function. So this is A. And this point here is A plus H in here. By the way, suppose I do not want to have this, there is a neighborhood around 0, etc., business. And if I want to let this A plus H to be an arbitrary point in U, then I can do that if I impose an additional hypothesis on U. What? Under what?
Path connected.
You see, path connectedness is not really enough, because what I need to do is I would like to apply Taylor's theorem on the entire. Okay, so let me just write this down and then you will see.
Convex.
Exactly, because you see, I need to have the entire straight line joining A to A plus H, all of that to lie within U. Because I'm going to use Taylor's theorem for this composite function. You use one variable, Taylor theorem, for composite 0, 1 goes to, let me just say A plus W inside U to R. So what does T go to? T goes to A plus T times H. And notice that this is the standard thing. You're fitting a straight line parameterized segment. When T is 0, I'm at A, and when T is 1, I'm at H. And all of this entirely needs to lie inside U, because I'm then calculating F on that. So this is going to F of A plus TH. So this is now just a function of a single real valued function of a single real variable T on the closed interval 0, 1. So I get to apply Taylor's theorem. Why is Taylor's theorem applicable over here? Come on, this is not difficult. In order for Taylor's theorem to be applicable up to a degree m, the function has to be continuously differentiable m minus 1 times, and the mth derivative has to exist, correct? So is that true for this composite function? G. Just look, no? In fact, f is given to be Cm. So what can we say about this composite function? F is a Cm function. So, okay, so G is this composite function is equal to G of T. But G is in fact a Cm function because F is Cm, and this function, it's a linear function. It's all C's that you want. C anything. It's C infinity, right? So is this clear? If I see if both, so what does chain rule tell me? If I compose two functions that are differentiable at the requisite points, then the composite also has a derivative. So let us say I have two C1 functions. If I compose them, the result is also going to be a C1 function, because the derivative of the composite is the composite of derivatives which exists, and both these derivatives are continuous, so their composition will also be a continuous function. And then you proceed in exactly the same fashion, right? So if I compose a C2 function with a C3 function, the result is going to be definitely a C2 function. All right, so I get to apply Taylor's theorem. And what does the formula become now? Everything is just really sort of scene setting, and then there is just one calculation to do. So what is f of A plus H is really what? G of
G of
come,
1.
let's at least set this up. Is G of what?
G of 1.
G of 1. And so by Taylor, what do I get to write it as? Summation k equal to 0 to m minus 1 of the kth derivatives of G at 0. So my reference point here is going to be 0, and I'm going to use that to evaluate the function. And then the last correction term, which is the mth derivative of G divided by m factorial, but now evaluated at some theta, correct? By the way, what happened to all those powers?
Powers of 1.
Yeah, they're all powers of 1, you see. So nothing for some theta in. So the key thing is to be able to calculate these derivatives of G. But G is a composite function, so I get to calculate the derivatives of G using chain rule. So thus we will be done by showing that the derivative of J, okay, so general, so G, kth derivative of G at 0. But why at 0? Let's just calculate it at t. Is going to be the summation of, all right. So let's work backwards a bit. So this is divided by k factorial, right? So, so I will be done if I show the following. I mean, sort of you should compare this term with what it is that we have stated up here. So comparing these, we will be done by showing the following. Summation S1 plus S2 plus up to Sn equals k of k factorial divided by product of Si factorials notice that in the one variable case I have k factorial in the denominator, whereas up there I have the product of Si factorials. So I'm simply adjusting by the requisite number, and then it should be d1 to the S1 up to dn to the Sn of f at a plus th times the same thing, h1 to the S1 up to hn to the Sn. When I plug in t equal to 0, notice that I will simply get this requisite partial derivative or evaluated at e. But now, by the combinatorial lemma, this is really the same thing as summation. I just realized that this partial derivative, when I permute the numbers 1 up to n, any which way, I'm going to get this partial derivatives that come in different or that are evaluated in different order. But by the equality of mixed partial derivatives, they were all giving the same number. So this is really the same thing as summation di1 di2 up to dik of f at a plus th times hi1 hi2 up to hik. Notice that if one is if among the I1 up to ik, one is coming S1 times, then that means H1 will come S1 times, no, among these H's, and so on and so forth. So here, okay, so we are almost out of time. So here the summation is over what? And if you're lost, I should tell you that you're lost only because of the notation. There is really nothing very serious going on. So this says that the summation over all I1 up to ik, where each one of the ones I1, I2 up to ik, each one of them is independently varying between 1 and n. So you see that so this this one over here. This is really just the number of ways in which I can take S1 ones, S2 twos up to Sn n's, such that the total number of things that I have taken is k. And the number that I have written here is just the number of, this is the multinomial coefficient, the number of ways in which all of these ones and twos and n's can be permuted among each other to give different permutations. So do this using, so since we are out of time, we sort of keep coming to it and then stopping. So do this using chain rule. Let's just see it for k equal to 1. Just so we do at least something. So for k equal to 1, what do I have? I want to have g prime of t, which is equal to d by dt of f of a plus t times h. What is that by using the chain rule?
T times, sorry, h times the total derivative of
Right.
f at a plus h.
Correct, exactly. So this is going to be, except you see, you have to say it the other way around. I made the same mistake, right? The map is going, sorry, where is the, yeah, so you see the map is going from first from 0, 1 to u and then to r. So the derivatives also have to go in the same way. That means first I have to take the derivative and that will give me h, and then to that I have to apply the next derivative. But when I write these, that means that h has to be written on the right. So this is really equal to f prime, the total derivative at a plus th, times d by dt of a plus th, which is equal to f prime a plus th times h. All right. But what does this really mean? Remember that these are matrices. So h is a vector. H is this vector, h1 up to hn. And f prime of a plus th is as a matrix. What is it? Remember, f is a map from dimension n to real numbers. So just like the example that we saw earlier, that was from 2 to 1. So the derivative of this is going to be a row matrix. And all the entries of this row matrix are going to be the partial derivatives of f along the principal directions evaluated at a plus th. So and f prime is equal to del by del x1 of, or let's just say d1, so that I do not have to write the names of the variables. d1f of a plus th up to dnf of a plus th. So when I use this over here, what do I get? I simply get summation. So I wrote f prime of a plus th, I should have written. So this is, so this really is just summation of di of f of a plus th times hi, summation over I going from 1 to n. So what is the value of k over here in this term?
1.
1. So now for k equal to 2, you should see what happens, but we are out of time, so we should stop. But please do this calculation and convince yourself that just the chain rule really gives me the expression. Okay, so let's stop.
Recording stopped.
Yeah, so So we still sort of fell short of finishing this, but please do try to do this on your own. One other thing that is left to do, or rather I would like to do, is to look again at this proof of equality of mixed partial derivatives. So that I will do next time, and we will do maybe a couple more examples. But please do work out the examples on your own. Remember, I have left for you to do this example 2, where I have written the thing. Now you do have to check that that this given function is differentiable, but that its derivative is not continuous. So those things I have asked you to check. And number 3, anyway, you have to do the problem on the homework. I'll do something analogous the next time. Okay, any questions?
Sir, just to confirm, the homework problems are the ones that are listed on Moodle, right?
Yes, exactly.
Okay.
So I think, let me just open it. Yeah, so homework will be posted on Moodle, and that's the official one. So homework 2, oh, sorry. Okay, I didn't realize. Yeah, I thought that this problem was assigned, but it is not assigned. It's a do for yourself problem. So the ones that I'm asking you to do are 5 problems from Rudin, 6, 7, 8, 10, and 13. And then there are 5 or 6 more problems that I have asked you to do. Five more problems. Yeah. So the one that I have in mind is the first bullet problem. The formula is xy square by x square plus y to the 4. That will give you something interesting.
Hello, sir.
So, yes.
Sir, could you just scroll up to the first example that you discussed in class today? I had a confusion.
Right. Okay. Here.
Yes, sir. So at the very first place, we show that f is continuous. I can understand that.
Right.
And after that, the del f by del x and del f by del y, I mean the partials,
Right.
they exist everywhere other than 0, 0. That is also something that I get. But after that, when we show that, I mean, we get at least one direction along which the del f by del x is not continuous, right?
Right. Right.
So from that, how do we conclude that f prime does not exist?
Okay. So does anybody want to answer that question? It is because of the theorem, our characterization of okay, or rather, okay, let's put it this way. Yeah. No, good point. Okay. So does anybody want to answer this question? So my first impulse was to say that, oh, but we know that f is C1 if and only if both the partial derivatives
Exist and are continuous.
And are continuous, right?
Yes.
But we are actually saying that f prime itself does not exist.
Yes, sir.
Right. Okay. All right. So let's go look at the thing and see if I got this right or not. So this bullet point, if f prime exists, then if f prime exists, so here it is failing for a simpler reason. If f prime exists, then remember it is a linear map.
Yes, sir. I mean, at every point, f dash gives us a linear map, right? I mean, f dash 0 is a linear map.
F dash, if f dash 0 were there, then it would need to be a linear map.
Yes,
right?
sir. Yes.
Now, okay. So let's put it this way. This linear map, what is the value of this linear map on the first standard basis vector?
So 0.
Because that's precisely the partial derivative in the first direction, right?
Yes, sir.
Okay. What is the okay, so I think okay, so there is, so my reasoning I think is defective over here. So let's go and examine this. All right. So likewise, the value of this linear map on the second basis vector is also 0. So if such a linear map did exist, its value on every single vector will have to be 0, right?
Yes, sir.
That means that the directional derivative in every direction must exist and be equal to 0.
Yes. Yes, sir.
Right?
Yes, sir. Yes.
Okay. All right. So let us see. Okay, so I think what I have written over here is correct. I'm not sure whether everything that I said in the class was right, because I said something about the limit. So let's examine. So that means I have to calculate the directional derivative and see that it is 0 in every single direction. That's
Sir, actually, I have a bit confusion in this point. I mean, f dash 0 is a linear map, right?
yes,
F dash 0 is a linear map. So, I mean, if it has the 0 matrix, then
right.
it evaluates, I mean, it gives 0 and on acting upon any basis. So, okay, sir. Yes. Now I
Right.
get it.
Right.
Yes, yes.
But you see, there is something to say over there. And the idea is that, so we did see this at one point, but we haven't talked a whole lot about the gradient. Okay. So see, here is the point. If you know how to calculate a linear map on basis vectors, then you know how to calculate it on any vector, right? Just
Yes.
by taking the same linear combination.
Yes, sir.
So there are two things that are being said here. So so this derivative on any vector must exist and its value must be 0. But not only that, and its value must be 0 because it must be a linear combination of the values of this
Basis
linear map on the
vectors.
basis vector. So it will have to be 0.
Yes.
The next thing that we are saying is that the value of this derivative on any vector v is precisely the directional derivative in the direction.
Okay.
Okay, so this
Okay.
is something I'm not sure whether we stated this explicitly in class, but this is
Oh,
something
okay,
that
sir. As because it's in the form of the ratio, so
right.
that's why, I mean, the direction ultimately matters. By what extent it scales, that gets cancelled out ultimately.
Right. So okay, so just one second. Right. So no, I was just remembering the formula for the derivative. So this has to happen. So the derivative is a linear map such that the requisite limit is equal to 0, where I'm subtracting from the difference quotient, I'm subtracting th, where t is supposed to be the derivative. But there's a small bit of work to see that the value of the total derivative on any vector v is precisely the directional derivative in the direction of that vector, corresponding to that vector. So now the calculation here does the job, that when I'm calculating the directional derivative at the origin, and I'm saying that this directional derivative, so what are we saying? So in fact, here what happens? Does this directional derivative exist?
No, sir.
Sorry, just one second. Now I'm confused a little bit over here. No, the directional derivative does exist, no?
Sir, the directional derivative is not continuous, actually. I mean,
but
from
that's
the calculation that we have done.
But you see, for the and in fact, this was sort of why your question was, it is good to have this question, because for the derivative to exist, it is not necessary that the directional derivatives be continuous.
Yes, sir.
Right. So
Yes.
from discontinuity of some directional derivative, I cannot really deduce that the derivative does not exist.
Yes, sir.
I can deduce the other way around.
Yes, sir, because the
Right.
differentiability implies
Right.
continuity.
No. That's a separate issue. Differentiability of f implies continuity of f. But what I'm saying is that if all the directional derivatives were continuous, then the total derivative would exist and be continuous.
Yes, sir. That is something we prove for C1
That is
functions.
something that we prove.
Yes.
So if we show that the derivative does not exist at a point, then of course some directional derivative has to be discontinuous, even if it existed.
Yes, sir.
Right.
Yes.
But the directional derivative existing for all directions does not imply that the function is differentiable.
Sir, nor does it imply that it is continuous.
Right. And in fact, exactly. So in fact, the examples that, so we need to see examples of that kind. Yes. So directional derivatives existing in all directions does not imply that the derivative exists, and in fact, as you said, it doesn't even, so that it is that just partial derivatives exist, but the function is not differentiable. That's all it is.
All right, sir.
Okay. Right. So sorry, just 1 second. I should really say, and is continuous away from origin. That therefore partial derivative, at least one must be discontinuous, and then we saw that it indeed is. Okay. Anything else?
Sir, the question about
Okay. And also, sorry, just one more
yes,
thing.
sir. Yes, sir.
I wanted to say that in Taylor's theorem, so in one variable Taylor's theorem, you know that for the remainder term, there are different ways of saying it, right? There is also an integral form of the remainder term, right? So did
Yes,
you
sir.
do this in the first semester for Taylor's theorem? Okay. So there is such a thing like that. I do not understand it fully, so I didn't talk about it. But there is such a version of Taylor's theorem also in the, and you can see why, no? Because the Taylor's theorem in multivariable case, we are just deducing it from the one variable case. So because we have an integral form, there must be something analogous. Right. Okay. So now go ahead, please.
So as I'm about to say this, I realize that I'm not super organized with this. But what I tried is, if we have a function from Rm to Rn,
Right.
and we take some arbitrary bases of both of these two spaces.
Okay.
The places where the proof could perhaps stop working.
But 1 second. So what is it that you want to prove? I mean, can you tell me what you are trying to achieve so that?
Oh, yes, sir. Yeah, I should have stated that first. If directional derivatives along any basis exist and are continuous, then F is C1.
Okay, right. Okay.
So the proof, we sort of walked along each of the axes by taking f of a1 plus h1 a2 and so on. We did that sort of a thing, and this still works no matter what basis we take as for our input space, because we still do this. We can still do the exact same thing of reducing to the one variable mean value theorem, and we can do that.
One question: should the basis be orthonormal or something?
I don't think so.
Okay.
Right. So in fact, let's just let's just expand on this small exchange here. You see, all that mattered was so how did we go from A to A plus H? I don't recall the terminology, but I think that's what it was. No, how did we go from A to A plus H?
So we walked along each of the quote unquote axes.
Right.
And here
so all that mattered was that I had a path, a piecewise linear path going from A to A plus H. Yeah.
Yes, sir. Yeah.
Did it matter that the legs of this path were perpendicular to each other anywhere in the proof?
Not here. I think it mattered near the end, but not here.
Okay.
So
go ahead now, please.
So none of so it does not matter anywhere here. At the very end, we wanted to show that, like, we had this particular dot product of h with our partial derivatives, and we wanted to divide that by norm of h and show that this quantity can be made very small. And how we did that was by using Cauchy-Schwarz. That does not directly hold here because we can't use, like, the dot product that we have here, like it's like we're taking sort of a point-wise product, but not with respect to the standard basis. So this is not the standard dot product anymore.
Mm-hmm. But okay, so the thing is, what is the limit in question?
So the limit is summation of, so if h is h1 comma h2 comma hn, and our variables are c1 through cn, the limit that we want is summation of hi times del f by del ci of some points vi, the ones that we chose along the path, divided by norm of h.
Correct. That is the quantity of which we are calculating the limit. What do we want to show this limit to be?
A 0.
So you see, the limit is being shown to be 0. Does the norm matter?
It does not. So we can just choose the norm that this bilinear form generates. And this is an inner product.
Okay, but I mean, we sort of should right. Okay, so I mean, so there is something to work out over there, right? But you see, right? But it does, right? So think about it, right?
No, sir, I think I do have a proof for that also. So I wanted to ask that also.
Yeah. So does everybody understand what it is that he's trying to accomplish? You should try to think of this for yourself. It really is I mean, it's sort of a combination of a bit of calculus with really linear algebra. Okay, so anything else?
Sorry, sir. Should I go ahead with what I thought was a proof for that, or should I?
I think maybe we can discuss that individually. So,
sir. Yeah. Okay, sir.
Because I want everybody else also to think about this. So,
okay.
Now here is one question that I have. Sorry. Okay. So I put this in quotation marks. No. Need to make sense of this in multivariable situation. Any idea how to make sense of this?
Can you repeat your question?
Yeah. So so you see what is on the screen, right? There is something in quotation marks. F of a plus h is equal to, that right hand side is within quotation marks. Because you see a plus h is a vector and f of a plus h is also a vector. So on the right hand side, if you examine each term, well, f of a is a vector, so it's good. F prime of a times h. Now that is not a product of numbers, right? So
I think we can view the higher derivatives as like so the kth derivative as a k linear map and h to the power k as the k tuple of h repeated k times.
Exactly, that is the thing. So you see, so that was, this last bit was the thing that was left. So when I say f double prime of a times h square, that f double prime of a is a map from f double prime of f double prime of a is a map from the ambient source vector space multiplied with itself. So Rn, so in this case, it is a map from Rn cross Rn to R. Right? So if I want to get a real number out of this, then I need to evaluate this. It happens to be a bilinear map. But if I want to evaluate this, then I need to supply two vectors from Rn. So this h square, if I interpret it as h comma h, then that's how to make sense of this. And likewise onwards, right? So triple derivative of a of f at a multiplied by h cube is really the triple derivative of f at a evaluated on the three tuple h comma h comma h. That's what it is. And you see, this makes complete sense if you compare it with what is happening down. Now this three tuple, let's just look at this three tuple. So what are going to be the components of this triple derivative? The components of this triple derivative are precisely going to be all the triple partial derivatives, dijk of f at a. Now, these three partial derivatives, so you see, if I think of this as the matrix of all partial derivatives, not matrix, some kind of, an array of, so the third derivative is going to be a three-dimensional array of all partial derivatives. Fourth total derivative will be a four-dimensional array of all partial derivatives, right? D, I, J, K, L of F. So what is that term saying? That each one of those partial derivatives, when I evaluate, so when let's say the third partial derivative, dijk of f at a. Now this partial derivative, I want to evaluate. If I want to evaluate it on, sorry, I'm the partial derivative is evaluated at e, but the matrix of these partial derivatives is evaluated on the vector h comma h comma h. This is going to be one large sort of matrix vector product. Right? The vector is also has multiple, multiple copies of vectors, and the matrix is also multidimensional. The way to, if you want to sort of make sense of this purely in terms of linear algebra, then the right language is tensor products. Okay, because tensor products turn multilinear maps into linear maps from the tensor product of those vector spaces. But you can sort of see that if the partner that will, when I apply the full triple derivative to the vector h comma h comma h, I'm going to get a large sum, and the partner of dijk of f evaluated at a in the vector part is precisely going to be what? The product of hi times hj times hk. That's how things are going to pair up, and then they're going to get added. That's how I'm getting this large sum. Just like in the first term, f prime of a times h, we saw that, no? F prime of a evaluated at h, when we wrote this down at the bottom here. Well, f prime of a plus th evaluated at h. You just take all the partials, and each one of the partial gets paired with hi when I take this product of row with the column. The same thing is going to happen in multiple dimensions. Okay, so I think if there is nothing else, then we will stop. In the next class, we will rewrite the proof of this equality of mixed partial derivatives, and I will do some more examples. As I said, we are not going to be doing any new theory this week. So